Hello, my name is Giulia Santoro. I was part of the 31st cycle of the PhD course in Electrical, Electronics and Communication Engineering, and now I'm working as a hardware design engineer in the Apple GPU Design Center located in London. My research is an exploration of new computing paradigms for data-intensive applications. The motivations behind this work are related to the computing model of modern processors that is based on the data exchange between the processing unit and the memory. This model has three main drawbacks. So, first of all, memories are significantly slower than processing units. They are the actual performance bottleneck. Also, memory accesses are extremely energy expensive. And this has a huge impact, especially on data intensive applications that are now used in our everyday life. For these reasons, the research community is looking for alternative computing paradigms, such as in memory computing. According to this model, data is computed directly inside the memory, so there's no need to move data back and forth between the processing unit and the memory. And this model has three main advantages. So there's no need to wait for the memory to provide the data. There's no waste at all of energy for accessing the memory because all data are computed locally inside the memory. And in terms of technology, so implementation, many of the alternative technologies that are now emerging over the conventional CMOS one are perfectly suited for this computing model, and we will see why. My approach to in-memory computing is CLIMA, which stands for Configurable Logic in-Memory Architecture. CLIMA is composed of a computing core, which is an in-memory array composed of different cells interconnected together and working in parallel. Its main features are parallelism, configurability, and flexibility. What gives CLIMA configurability is the cell, which is the fundamental building block of the architecture. The cell was designed to be configurable, which means that the same hardware can be reused to support different arithmetic and logic functions. It is modular, so the cell can be easily replicated to build bigger arrays, so the architecture is highly scalable, and it is also characterized by variable complexity, which means that multiple cells can be embedded together to form more complex cells that support more complex functions. The type of in-memory operations that CLIMA supports are three. So data can be computed locally inside each cell, or they can be computed between cells on different rows or columns, or between cells on the same row or column. Now, in particular, these last two types of in-memory operations are what makes CLIMA highly flexible and capable to support complex data flows and complex applications such as, for example, convolutional neural networks. In terms of implementation, CLIMA is perfectly fit for emerging magnetic technologies such as nanomagnetic logic. This technology, in fact, provides at the same time non-volatility, intrinsic in-memory computing capabilities, 3D integrability, and a very low power consumption. So for all these reasons, CLIMA was implemented by using the NML technology, and this picture shows the NML layout of the single cell. Now, the results, when comparing CLIMA to a conventional non-in-memory architecture, what we get is a 75% average performance improvement thanks to the high parallelism of CLIMA, 2,000 times memory access reductions thanks to the data reuse possibilities offered by this architecture, and a 50,000 times power density reduction thanks to the use of nanomagnetic logic. So these results clearly demonstrate the effectiveness of the CLIMA approach and of the in-memory computing paradigm. So this concludes my presentation, and thank you for listening.